My name is Alfredo Chaparro, and her name is Rosa Lopez, and we're gonna go ahead and explain real quick chapter 17, okay? Okay, chapter 17 starts with the three laws of thermodynamics, which are number one is the energy cannot be created nor destroyed, it can only change forms. So let's give you a quick example. So let's say we have a coffee, right? Let's say we have a coffee mug. Oh, this one's not working, so let's get another one. So let's say we have a coffee mug with hot coffee. So normally this one's a high temperature. So let's say it has a temperature of 75 Fahrenheit, right? So but it's losing heat, it's losing vapor. So all that heat, all that temperature, it's not leaving, it's not destroying, it's not disappearing, it's not coming back ever. It's just escaping to the cold room around it. So the energy of the heat, it's just going to the surroundings of the room. So energy does not, it's not destroyed, it's just transformed into another type of energy. The second law of thermodynamics says the entropy of an isolated system not in equilibrium will tend to increase over time, approaching a maximum value at equilibrium. So a little easier definition of entropy is the degree of disorder in a system, okay? So an example is that the entropy of the universe is slowly expanding. So since the universe is expanding, so we have a universe, and universe is always expanding over time. That means the entropy of the universe is also expanding over time. Also now the third and last law of thermodynamics is as temperature approaches absolute zero, the entropy of a system approaches a constant minimum. Okay, and those are the three laws of thermodynamics.
So I'm going to talk about spontaneous processes. What is spontaneous processes is a spontaneous reaction doesn't happen like instantaneously or fast. The definition is that it occurs under a certain type of conditions, and they are more visible, like water, like a waterfall, water falling downward, or sugar getting dissolved in coffee, or or even freezing of water. So what happens when we have a spontaneous reaction? So this is a tube, and this is a closed valve, and we have certain particles here. And then when we have a spontaneous reaction, and we open the valve, the particles spread evenly throughout the tube, taking up every space that is within this particular area.
Okay, I'm going to continue talking a little bit more about entropy since it's a really important part of the chapter. So since the whole chapter is basically on entropy, so I'm going to go ahead and give you an example of what entropy is. Okay, I'm going to continue talking a little bit more entropy. So since the chapter is basically on entropy, I'm going to go ahead and give you an example of entropy so you more or less know what it is. So let's say we have a baseball that's flying through the air. Let me draw that baseball right there. Okay, so it's flying through the air. So it starts off with its energy organized, its energy balanced. So as it moves through the air, as it's moving through the air at certain velocity, it's moving through it, it's losing kinetic energy because of the air resistance, because of the change of kinetic to potential. So it's losing kinetic energy into the air itself, into the particles in the air. So it's being distributed, all this energy is being distributed to the particles in the air, so that the total energy of the system, because of this, has increased. Okay, so also there's another example so you can more or less understand entropy. So it's called phase change. Okay, and remember that entropy is the degree of disorder in a system. So I'll get right to that. So let me go ahead and explain phase change. So we have phase change, what it's called. And I'm going to draw some pictures so you more or less understand what I'm talking about. So let's say we have a rectangle. Okay, so we have a rectangle with a point. So, and then okay, let me just erase that real quick. So the phase change, this box is like a graph, but the point in a graph represents a whole state of a system. So let's say these it has this little point means it has four particles. Okay, so four particles. So each particle has a different color. So let's say this one's red. Let's say this one's yellow, green, and blue. Okay, and they're in the corner of the box. So we have a rectangle, right? And we have a rectangle. This point represents the whole state of a system. So let's draw a system. Let's say we have four particles in the system in this little dot, and each one has a different color. We have a red, yellow, green, and blue, and they're in the corner of the box. So there are multiple combinations of this system. There's multiple combinations that you can do with each color, right? So you can go ahead and do. You can go ahead and change the colors up, and let's go ahead and put blue here. Let's go ahead and put green here, and then red and yellow. And then we have another combination that you can go ahead and make, which is red, green, blue, yellow. And then we have another combination that we can go ahead and make on this. It's going to be green, blue, red, and yellow. And then we have just the last combination that we're going to, because you can go ahead and make almost 16 combinations. And let's go ahead and just say we can go ahead and do red, yellow, green, and blue. Okay, so you have these combinations that you can go ahead and make out of 16. So they each represent a point in the phase. So they all represent a point in the phase change. Okay. Okay, we have 5 layouts of 4 particles with 11 combinations more possible. Okay, so we have a total of 16 combinations that we can go ahead and make. Okay, each combination is different from the other, and each one makes a point in the phase change. Okay, so in total you would have a total of 16 states, each one different from the other one, and that would make they're all undistinguishable because they're all different. So this is an abstract representation of more or less what entropy is in the system. So you would have your phase change, and each one would be a state. So you have a total of different states in your whole system, and they're all in disorder. I mean, they're not all perfect. They're not all the same. So they change a little bit back, but at the end, this disorder is what makes up entropy. Okay, so we have the basic formula for entropy is S equals K log of V. Okay, so N stands for entropy, and then K is the Boltzmann constant, which is 1.38 to the negative 20. To the negative 23. So this is the K constant, and then V is the volume of the box in the phase change, the box we just looked at right now, the system. Okay, so this is a basic formula for entropy. Entropy can also be defined by another formula, so which is S equals Q over T. Okay, so here is S equals a change in entropy, and then we have Q, which it could be either work or heat, and then we have T, which is the change in temperature or the constant temperature in the system. Okay, so this is another way that it can be defined.
Okay, so I'm going to talk about the second law of thermodynamics. So what is the second law of thermodynamics? It is, well, according to the book, is the entropy of the universe increased in a spontaneous process and remains unchanged in an equilibrium process. So the way we can calculate this is for a spontaneous reaction, we have delta S of the universe, that makes sense, which is a change in entropy in the system. There's a change in entropy of the surrounding areas. This has to equal 0. Since the universe is made up of the system and the surrounding areas, it has to equal 0. For non-spontaneous, we have the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings is equal to 0. It's equal to 0. For the spontaneous reaction, it doesn't matter if the charges are negative or positive. What matters is that this number has to be greater than 0. So what happens if we have entropy change in a system? We have to use a equation, which is the standard entropy of reaction equation, which is the change of the reaction is equal to the sum of the products minus the sum of the reagents. So we're going to go ahead and do an example of this so we can practice a little bit more with this equation. So let's say we have N2 plus 3H2 is equal to 2NH3. So in order to get the individual values of each, in the book that we are using, you should go to Appendix 3 to get the values of each of the individual molecules. Okay, so according to the book, N2 was 192, H2 was 131, and then NH3 is equal to 193. So the way the equation is going to look, it's going to look like this. So remember that the equation is the sum of the products and mine is the sum of the reagents. So, and since H2 has a coefficient of 3 and NH3 has a coefficient of 2, you have to multiply this number by this number to get the total of the moles. So it's products first. So these are your products, and these are your reactants. So the value of NH3 is 183. And don't forget the 2 because there's 2 moles of 2NH3. So we're going to go ahead and multiply 2 times 183, which is minus the 192 because we only have 1 nitrogen, plus the 3 moles of hydrogen, which we are going to multiply by 131 to get the total reaction. So once you calculate this in your calculator and everything, we get a total of negative 199 joules per Kelvin or mole. And this is the answer, and this is how to practice and calculate how to use the standard entropy change reaction. So we have a certain rules that apply to entropy change. So these rules vary within what type of equation or what type of charges you have. So if the reaction produces more gas molecules, so if we have more gas molecules, the change in entropy is will be positive. So yes, so it's more gas molecules. If we have more gas molecules, the change in entropy is going to be positive. The next rule is if there's no gas left, if some way there's no gas left in the reaction, the change in entropy is going to be negative. So if we have no gas molecules, the change in entropy is going to be negative. And the third last rule is if there's no net charge, excuse me, there's no net charge, it can be positive or negative. It doesn't matter what, as long as there's no net charge, it doesn't matter if it's positive or if it's negative. So no net charge equal to positive or negative. So now we have the third law of thermodynamics, which is the entropy of a perfect crystalline substance is zero at the absolute zero of the temperature. The third law helps us identify the absolute entropies of the system. And for this, the book stated an equation that was change in entropy equals to entropy to SF, it's entropy, minus SI, and it equals the SF. So with the third law, it had a diagram that stated, I guess, physical states or matters, the physical matters, like the gas, solids, and everything. So we have here temperature, we have entropy by moles, and then here we start as a solid, and then it goes up, and then it increases. At this point, this is your melting point. Let's put this here. And then from here, it goes back to the slanted line, which this is your liquid. And then it goes back up. This is your boiling point. And then it goes to gas, to the last form of this. Okay, so we're gonna work a little bit more on the standard entropy of reaction. This is another example, which is CaCO3 and CaO plus carbon dioxide. So this is the equation we're gonna use to calculate the the change in the standard reaction. So first we're gonna identify the numbers, which are given in the book in the appendix 3. So now we're gonna just substitute the numbers. So we have the products, and this is your product, and these are your reagents. No, sorry. These are your reactants, and these are your products. So we're gonna substitute the products, which is CaO is 39.8 plus CO2, which is 213.6, minus the reactant, which is 92.9. And once we do this calculation, we're gonna end up with 160.5 joules per K times mole.
Like that? Okay, next is we're going to talk a little bit about Gibbs free energy. So the second law of thermodynamics states that a spontaneous reaction increases the entropy of the universe, okay? So let me write that down for you. So S, the universe. Okay, so we have a basic formula for the entropy of the universe. So it's going to be the change in the entropy of the universe is equal to the change of the entropy of the system plus the change in the entropy of the surroundings. And all this has to be greater than 0. Okay, so a spontaneous process is one that occurs without the addition of external energy. Okay, so it may be short, it may be long, because it's not related to kinetics or reaction rate. Okay, so an example, and a really vivid example, is the process of diamonds and carbon. So the process of from a diamond to a carbon takes a lot of years. It's really not it's not even in like visual time scales. You can't really sit down and just wait for a diamond to transfer to graphite or a carbon to change to a diamond. So you kind of have it's a really long process. So that's why people say that diamonds are forever, because they're really long processes. So we have that example, and spontaneous process can be exothermic or endothermic. This is not really related to enthalpy changes, so it's really by itself. And so we have this equation, which is the change of enthalpy of the universe, or so we will use this formula if you're trying to calculate the entropy of the whole universe, which we don't really care about it, because in chemistry we only really care about like the changes in a beaker, or maybe the changes in the system, or the changes of enthalpy in the system, or something smaller than the whole universe. So that's why free Gibbs energy was created. So we don't really want to know the entropy of the universe. We just need to find the changes within our system. Okay. So that's why we're gonna go ahead and write down what the free Gibbs energy is. Okay. So let me just erase this real quick for you. And in the free Gibbs energy, we go ahead and change two of the values. So when a process occurs at a constant temperature and pressure, we rearrange the second law of thermodynamics, and we write it as such. So it's G equals H minus T S. Okay, so this is the free Gibbs formula. Okay, so G obviously stands for free Gibbs formula. Free Gibbs, my bad. H stands for enthalpy, or the change in enthalpy, and then T is the constant temperature, or the change in temperature, and S stands for entropy. Okay, so and all this is in K J over mole Rxn units. Okay, so this is how we're gonna go ahead and use to find the change in energy. We're gonna go ahead and use the free Gibbs energy. So normally they'll go ahead and give you the enthalpy, or they're going to get and give you the change in enthalpy. and then you go ahead and subtract it by multiplying the values of the constant temperature and the entropy. Okay, so all this is always going to be in kilojoules per mole in the reaction. Okay, so this is the units that we're going to go ahead and use for any problem as the example follows. Okay, now we're going to go ahead and do a free Gibbs energy example. Okay, so we have an example says that at 298 kelvins, the change in G is negative 190.5 kilojoules, and the change in H, the enthalpy, is negative 184.6 kilojoules. And then for the reaction, we have H2 gas plus chloride gas, 2, yeah, and it becomes HCl gas. Okay, so if we have to calculate the standard entropy for the reaction. Okay, so our formula is G, the change in G, the change in H, enthalpy, minus temperature and the change of S. Okay, so right now we go ahead and plug the values are given. We have G, so it's 190.5 kilojoules. Remember units always. Times the change in enthalpy, which is 184, negative 184.6 kilojoules, minus temperature. Okay, temperature is given at 298 kelvin. Remember, absolute temperature, no Celsius. And or change in entropy. Okay, so we should go ahead and solve for S. And our answer should be, it's going to be 0.020 kilojoules per Kelvin. Okay, so if you want to go ahead and just round this off, it's going to be 20 kelvins per Kelvin. Okay, so you should be getting this answer.
So this is an example of free energy and chemical equilibrium. We're going to use this equation to calculate the delta G. So the delta G in the example is given to us, which is 5.4 kilojoules per mole. And then our R is a rate constant, which is 8.3414. And our Q is our quotient, which is the products over the reactants. In this case, it's going to be 0.22 over 453. So the total equation is going to look like this. So we're going to have 5.40 times 10 to the third plus the rate constant, which is 8.314, times the temperature, which is at 25 degrees Celsius, is equal to 298 Kelvin. Times the log, I'm going to put it over here since I ran out of space, times the log of the quotient, which is 0.22 over 0.453. And don't forget the exponent number 2, since our equation is N2O4, it's a reverse reaction. It's equal to 2NO2. So this 2 is our exponent on this one. So once you have that, you're gonna calculate, and then we're left with 5.40 times 10 to the third minus 8.46 times 10 to the third. So we're gonna go ahead and calculate this, and it's equal to negative 3.06 times 10 to the third, which is the same as negative 3.06 kilojoules per mole.